All right, hi everyone. This is Larry Mussolino. I'm recording a part two video. This is for Math 241. This is the Module 4 homework. So I did post a Module 1 video with a few examples, but I wanted to do a few more here from kind of the second half of the homework. So I'm coming here to number 15 on the homework. It says here, find dy dx. Remember, dy dx is notation for the derivative function. And remember, you could also think of this as y prime, f prime x. All of these mean the same thing in terms of finding the derivative. Well, for this example, we're going to need the quotient rule here. Why do we need the quotient rule? Well, if the function you're starting with is a fraction like this, where there's a function of x on top and a function of x on the bottom, that is where we need the quotient rule. So let me start out writing the quotient rule, and then we can plug into that. So the quotient rule says, if you want to find the derivative function, dy dx, and you label the top of the fraction as the f function, label the bottom of the function as the g function. The other thing we're going to need here is the derivative of these trig functions. Well, it turns out the derivative, if y is sine x, then its derivative is cosine x. But if the original function is cosine, the derivative is negative sine. So we're going to need those derivative rules for trig functions. All right, what about the quotient rule? The quotient rule says take g times f prime minus f times g prime all over g squared. So let me write down the f function. We labeled that as the top of the fraction, so that's 9 cosine x. G we labeled as the bottom, 1 minus sine x. Let's go ahead and find these derivatives so we could plug into the quotient rule. How about the derivative of 9 cosine x? Well, 9 is a constant in front, you copy it. The derivative of cosine is negative sine. So I'm going to write this as negative 9 sine x. All right, how about g prime? The derivative of 1, this is a constant by itself, that's 0, minus the derivative of sine is cosine. So this is going to be negative cosine x. All right, let me go ahead and plug into the quotient rule. So we need the g function to start with. So this is dy dx. The g function. Our g function was 1 minus sine x. Now we need f prime. Our f prime was negative 9 sine x. All right, subtract the f function. Our f function was 9 cosine x. And last, we need g prime. G prime was down here, negative cosine x. And this is all over g squared, which is 1 minus sine x quantity squared. All right, let's do a little bit of algebra cleanup here. Let me go on the top, and I'm going to multiply this negative 9 sine x inside the parentheses. So that's going to be negative 9 sine x plus 9 sine squared x. Now, when you write sine x times sine x, you can either write it as sine x in parentheses squared, but sometimes you put the exponent 2 with the sign. So this is usually the way you'll write it. All right, let me come back here. Now, this is a subtract a negative back here, so that's going to flip to be positive. 9 cosine squared x all over 1 minus sine x squared. Well, there's a very famous trig identity, trig formula that says the sine squared of an angle plus the cosine squared of the same angle, this is always equal to 1. So let me factor out a 9 back here. So this is going to be negative 9 sine x plus 9 sine squared plus cosine squared. But this parenthesis back here is a 1. So here's what I'm left with. Let me write it up here maybe. What we're left with is, this is dy dx we're working on right now. All right, I'm going to factor out a 9 from the top here. So if I take out a 9, it's going to be negative sine x plus 1 over 1 minus sine x squared. But this negative sine x plus 1, I could just rewrite that as 1 minus sine x. And notice this 1 minus sine x is going to cancel out top and bottom. So this parenthesis 1 minus sine x on top cancels out one of those factors in the denominator. So here's my final answer, 9 over 1 minus sine x. All right, so this was the quotient rule we needed here. And you needed to remember this famous identity from trig, that sine squared plus cosine squared equals 1. All right, let me jump to another example here. All right, let's do something here. This is a little different because it is, the notation here is a little tricky. All right, so they're giving us this function y equals the square root. And they're going to ask us to find dy dx. Well, for this example, we're going to need a rule called the chain rule. Now, they're going to walk us through this chain rule. They're going to kind of guide us. And so it says, write the function in the form y equals f of u. Well, they want me to really use u as the quantity under the square root. Remember, they want the variable to be u, y equals f of u. So really the way I'm going to write this is y equals the square root of u. If I write it that way, I'm really defining u to be this expression under the parenthesis, which is 8x squared plus 5x plus 6. So here is the answer for part A. All right, let's go to part B. Part B says find dy dx. Well, there's a way to write the chain rule. What I could do is find dy du and then du dx. So if I find dy du and multiply it by du dx, you can kind of see that these du's would cancel out, leaving me dy dx. All right, let's do it. So this y equals square root of u. I can think of it as y equals u to the 1/2. Remember, the square root is the same as the exponent 1/2. That was an algebra effect. So let's work out dy du. Dy du, this is the power rule. It would be 1/2 u. Now I got to subtract 1 from the original exponent, negative 1/2. Now I like to get rid of negative exponents here, so I could write this. Let me make this clear. It's negative 1/2 up here. I could write this as 1/2 1 over 2 u to the 1/2. I'm moving that negative exponent down to the bottom of the fraction. That changes the exponent to be a positive exponent. That's, again, an algebra effect. All right, so we just figured out this is 1 over 2 u to the 1/2. All right, now we need du dx. Well, here's u. Du dx would be using the power rule here. This 2 comes down in front, multiplies the 8. That's 16x. The derivative of x is 1, so that's 16x plus 5. So this is going to be 16x plus 5. The only last item is I'm going to substitute for u this expression that we started with. So here's the final answer. dy dx is 16x plus 5. On the bottom, 2u to the 1/2. Well, I could write that as 8x squared plus 5x plus 6 to the 1/2. If you wanted to, you could replace the exponent 1/2 with square root. So another way you could write this answer is using a square root in the denominator. So 16x plus 5 over 2 square root 8x squared plus 5x plus 6. So this process of thinking of dy dx as dy du times du dx, this is the chain rule. All right, let's do another example like that. All right, here's an example. It says y equals 3x, dx dt equals 5. And they're asking us to find dy dt. Well, the way I can think of this is think of this as dy dx times dx dt. Again, notice if you think about canceling out dx top and bottom, you would be left with dy over dt, which is what we want. All right, let's work out dy dx. That's the derivative of this y function with respect to x. Well, bring the 3 with me. The derivative of x is 1, so that's just 3. So this is a 3. dx dt they gave me. They told me that was 5. So this is simple. This is 3 times 5. The answer here is 50. Okay, folks, so some of these examples involve what's called the chain rule. All right, hope this is helpful as you're working in Module 4 homework. Again, please let me know if you have any questions or if I can help in any